This program will look at hybridization in multiple bonded compounds. I want to start by considering ethene, S2.2.15. I'll begin with the ground state of the carbons. They would have this arrangement with 2 electrons in the 2s and 1 in 2 of the 2p orbits, and 1 is vacant. We begin by promoting an electron. So an electron moves from the 2s up into the 2p. Our next step is to form a hybrid. But which hybrid do we form? For that we consult the Lewis dot diagram. Here around each carbon we see 3 electron regions. 3 electron regions dictate we're going to form an sp2 hybrid. So the electrons that will blend together to make our hybrid will be these. So the 3 orbits mix and the 3 electrons split amongst them, and we get this configuration, leaving 1 electron in the 2p. The sp2 hybrid has a trigonal planar shape with 120 degrees between each of its orbits. 2 of these orbits will be bonded to hydrogens, and another one will then be bonded to the neighboring carbon. That neighboring carbon will also have 2 hydrogens attached to it. So at this point we can see the formation of 5 sigma bonds, where our hybrid orbital is overlapped on its ends. This is the top view of the molecule. Let's rotate it now and look at it from its side view. This is where our 2p electron will come into play. It exists in electron clouds above and below the plane of the molecule. So this shows the electron cloud for, say, the carbon on the left, and the carbon on the right is in a similar situation. Where these orbitals overlap, we form what is called one pi bond. Pi bonds result from the overlap of p orbitals on their side. So when we see a double bond in a compound, it's actually a sigma bond and one pi bond. Let's consider the molecule ethyne, C2H2. Again, we start with our ground state carbons. We promote an electron, and this time the hybrid we formed, we can see, has 2 regions. 2 regions dictate we'll form an sp hybrid. So only these orbitals will be blended, giving the following configuration. The 2p orbits that weren't involved still contain 1 electron. An sp hybrid has this shape with 2 lobes. One of them is then occupied with a hydrogen and the other with the neighboring carbon. That neighboring carbon also has a hydrogen attached to it. So we can see in this case 3 sigma bonds forming. Let's take this molecule now and take a look at what happens with the 2p orbits. So again, perpendicular to the plane of the molecule, we have a 2p orbital. Each carbon has a 2p orbital that's half full. They then overlap, forming one pi bond. But we have a second p orbital that also is not bonded. This lies, I'm going to show, in the x-plane of the molecule, coming in and out of the plane of the slide. And there's 2 of them, 1 from each carbon. And these 2 overlap on their sides, creating a second pi bond. As a result, a triple bond is actually a sigma bond and 2 pi bonds. Let's look at a question involving this idea. Which of the following best describes the hybrids formed by the carbon and oxygen, as well as the bond types in the molecule with the following structural formula? First off, let's identify the bond types. Between the carbon and the hydrogen, we have a single bond, a sigma bond. Between the carbon and the oxygen, a double bond, hence a sigma bond and a pi bond. This leads us to options A and D. In order to determine the type of hybrid, we need some knowledge of the number of electron regions. For that, we need a Lewis dot diagram. The structural formula we have here doesn't show the unbonded pairs, so we need to add those. Oxygen would have 2 unbonded pairs, as 2 are involved in the double bond. Here we can see around the carbon 3 electron regions, an sp2 hybrid. Around the oxygen, a similar 3 regions and an sp2 hybrid. That leads us to option D. As a final note, I'd like to compare the strength of sigma and pi bonds briefly. Here I'm going to look at the carbon-carbon bond. In the single bond from our IB data booklet, we can see that it's 346 kilojoules per mole. The addition of the pi bond increases it by 268. It's not twice as strong. In fact, it increases by slightly less than twice. This indicates that the pi bond provided about 268 kilojoules of strength. In the case of a triple bond, again we add another pi bond and it went up by about 225. So in general we can see that a sigma bond is stronger than a pi bond. Questions are always welcome. Thanks for watching.